Okay, so for an example, if de Broglie accelerated an electron from rest using a 200-volt potential difference, what wavelength should he use for the double slit experiment? So, a little bit of unit 2 here. So let's just think about where we're going. We need to get from here, or we're going to end up there anyway, right? We need to get the wavelength. So, got the mass of an electron, but we need the speed of the electron here too, okay? So, how are we going to get the speed? Well, we have the voltage. So, if we apply physics principle number 5, then we have an electron in a place where there's a potential difference. In other words, an electron is going to have potential energy, right? So what's the potential, the electric potential energy? Well, that's QV will equal the velocity it ends up with, okay, over 2. Okay, we're ready to plug in. And that's the speed I got, pretty quick. But now we're ready to just go. Okay. Times that one I just found. Okay, so that also means his slits should be about that far apart. So you should try to find an atom with about that slit spacing. All right, an electron beam is diffracted by a crystal with a ion separation of 1.10 times 10 to the negative 10 meters. So that is what? Yeah, that's D. The diffracted electrons are seen on a screen 25 centimeters from the crystal. So a screen 25 centimeters from the crystal, hey, that's the length. And the resulting rings are 73 millimeters apart. Okay, that's X, but let's draw our picture to visualize what's going on. So we have a beam of electrons, right, coming in. Okay, they're going to get diffracted through a crystal with a spacing of D. Okay, and then what ends up happening? Well, they end up producing dark and light bands. They end up producing a lot of electrons and not a lot of electrons, right? So we end up seeing a whole bunch of electrons incident here and here on our screen here. Okay, so this would be our n equals 0, our central max. And then n equals 1 and 2 on either side. And it's saying that the resulting rings are 73 millimeters apart. So from this center here to the first ring, you get 73 millimeters apart. So what is that? That is X, okay, or 73 millimeters. So what do we need? If we're going to plug them into our double slit equation, we'd have N, it's 1. We have D. We don't have theta, but we can find it because we also know L, right? So tan theta would be X over L. So let's first find theta. And sorry, I got ahead of myself. Why are we doing this? Because we're trying to find the energy of the incoming electrons. Now, to get the energy of electrons, they're massive. So should we use hc over lambda or mv squared over 2? Right, we should use mv squared over 2. Okay, problem is, and you might be thinking, why are we doing this? This isn't going to give us V. Well, it will because they're behaving as waves here. And so we can do that to get V, right? If we have the wavelength. So tan to the negative 1 of 0. Be careful here, centimeters and millimeters. So 0.073 meters for millimeters and 0.25 meters for centimeters. I got 16.3 degrees. So now we're ready to plug in. Okay, so that's its de Broglie wavelength. These electrons are behaving as though they were waves with that wavelength, which means we can then go over here to get V. And rearranging, we get that. And I got they were moving at. Okay, again, a significant portion of the speed of light. So if you were in a university course, you would have to adjust this and reconsider and use relativistic equations, but works well enough for us now. So let's do the final step, find the energy. And I got that they have an energy of 2.5 to 2 sig digs times 10 to the negative 16 joules. Okay, now what voltage accelerated them? Well, how did they get that much energy? They had to go through a potential difference, right? So reminder, right? They got that energy because some electric field gave them that energy by exerting a force on them and accelerating them, right? How do we figure it out? Well, take the potential difference, the joules per coulomb, and multiply it by the number of coulombs. Except we're looking for the potential difference. We have the energy gained. We just found it, so plug in. All right, particles have wave properties, and guess what? You're a particle, okay? So you're a wave, right? Wave-particle duality, you are both. Calculate the wavelength of a 65 kilogram student running at 5 meters per second. So can we figure out lambda? Again, this is not on your formula sheet. You have to either memorize or derive it from the fact that P equals P, but we're ready to just plug in already. 2.04 times 10 to the negative 36 meters. Okay, so this is actually about 1% of a Planck length. So you see why the world does not seem to be very quantum for you, right? That your wavelength is smaller than something that's even actually meaningful to talk about in terms of length. So yeah, you've got a de Broglie wavelength, but it's so small that the smallest thing we can even meaningfully conceptualize in physics is 100 times bigger than it. Okay, so nothing exists that's small, but even on a more practical matter, how are you going to fit through a space that small, right? So that is why we cannot do a diffraction experiment. No slit that small exists, as far as we know anyway, okay? And even if it did, you sure as heck wouldn't fit through it. Okay, so that really wraps up topic 4 and therefore unit 3. Okay, so if you want practice, try out the questions that go with this from the agenda or the Google Classroom. And if you're feeling good about all that, you ask me any questions. I mean, feel good, I guess, is kind of a relative term. There's been a lot of changes for you this week in physics, right? We've kind of thrown out a couple hundred years worth of classical physics. So if you feel as good as you can about this stuff, then you're ready for the summative weekly check-in. Okay, have a great weekend.